Hello everyone. In this transforms lecture, we are going to see some properties and theorems on Z transform. So first we will see the properties. In that we will consider let. Suppose the given sequence is f of n and its Z transform is f of z, which is defined using this formula. Similarly, we consider another sequence, say g of n, whose Z transform is given by this formula and we denote it by g of z. So first property is linearity property, which is defined as Z transform of sum of two sequences f of n and g of n is equal to the Z transform of sum of Z transform of that two sequences, that is A into Z transform of f of n plus B into Z transform of g of n, where A and B, they are scalars. Second property is change of scale property. It is given by Z transform of the sequence A raised to n into f of n is equal to f of z upon a, and this term will be evaluated as f of z. In that, replace z by z upon a, where this f of z is the Z transform of the sequence f of n, which is given thing to us. To prove this, consider f of z upon a and apply the definition of Z transform. So it will give us summation n runs from minus infinity to infinity f of n z upon a raised to minus n. Simplify this expression. It will give us a raised to n into f of n z raised to minus n. Now treat this a raised to n f of n as one term and again use the definition of Z transform. So that will give us Z transform of a raised to n into f of n, which is the required result. Next one is the damping rule, that is the change of scale property only. In this, it is defined as Z transform of a raised to minus n f of n is equal to f of a z. And how to get this? In the Z transform of f of n, that is f of z, replace z by az. So that will give us the Z transform of the sequence a raised to minus n into f of n. Next property is the shifting property. For both sided sequence, it is defined as Z transform of the sequence f of n plus minus k is equal to z raised to plus minus k f of z, where f of z is the Z transform of the sequence f of n. To prove this, we will consider only the left shift property, that is Z transform of f of n plus k is equal to summation. By definition of Z transform, we will be getting summation n runs from minus infinity to infinity f of n plus k z raised to minus n. Now, we multiply and divide by z raised to k. That will give us z raised to k into summation n runs from minus infinity to infinity f of n plus k z raised to minus n plus k. Now to express it into the standard form of the definition of Z transform, we will replace this n plus k by r, and therefore as n tends to minus infinity, r tends to minus infinity, and as n tends to infinity, r tends to infinity, isn't it? K is any finite constant, and therefore we will be getting Z transform of f of k plus n plus k as equal to z raised to k summation r runs from minus infinity to infinity f of r z raised to minus r, which is nothing but the definition of Z transform. So it gives us z raised to k f of z. So this is the left shifting property. In same way, we will be getting right shifting property, that is Z transform of f of n minus k is equal to z raised to minus k f of z. In same way, for one-sided sequence, for n greater equal 0, Z transform is given by Z transform of f of n plus k is equal to z raised to k into f of z minus summation r raised from 0 to k minus 1 f of r z raised to k minus r. So this is for one-sided sequence, left shift property. Now, one-sided sequence for n less than 0, then z transform of f of n minus k, right shift property, it is given by z raised to minus k f of z plus summation r raised from minus k to minus 1 f of r z raised to minus k minus r. So this is for one-sided sequences for n greater equal 0 and for n less than 0. And last one for causal sequence, the z transform of f of n plus k is given by z raised to k f of z minus summation r equal to 0 to k minus 1 f of r z raised to k minus r. And for the left shift property, right shift property, it is given by z transform of f of n minus k is equal to z raised to minus k f of z. So this is for causal sequence. Now we will see the property multiplication by n. So that will give us z transform of n raised to k into f of n is equal to. So this z transform of this sequence is given by minus z into d by dz bracket raised to k f of z. Means what we are supposed to do? We have to obtain the derivative of the f of z k times, considering these brackets k times, and then we have to evaluate the derivative one by one. To see the proof of this, we will start with k is equal to 1. So for k equal to 1, z transform of n into f of n is equal to summation n runs over minus infinity to infinity n into f of n z raised to minus n. So this is by definition of z transform. Now we will rearrange the terms. We will consider this n with z raised to minus n, and we will take one z outside, and we will multiply and divide by minus 1, so that we will be getting minus z into summation n runs over minus infinity to infinity f of n minus n z raised to minus n minus 1. So see, same term we have rewritten like this. Now if we observe this term inside the summation sign, then we can easily replace this term by d upon dz z raised to minus n. See, derivative of z raised to minus n will be minus n into z raised to minus n minus 1. Now, using the properties, we can take out this d upon dz term outside, and we can write down this as minus z into d upon dz, and whatever we left with inside the summation sign, f of n into z raised to minus n will be replaced by f of z. So see, when k is equal to 1, our result is true. For k equal to 2, z transform of n square f of n is equal to, it is obtained as minus z d by dz into minus z d by dz of f of z. Means we have to operate this operator one by one on f of z. So here we will note down the things related to this property. That first one is minus z into d upon dz bracket raised to k, it is not same as that of minus 1 raised to k z raised to k d raised to k upon dz raised to k, that is kth derivative. So it's not like that. Means what we are supposed to do, for example, minus z into d by dz bracket square of f of z, it will be evaluated like this. Operate the operator one by one number of times the power is. Therefore, minus z into d by dz of minus z into d by dz of f of z. So operate this operator first on f of z, multiply the result by minus z, then evaluate the derivative of result with respect to z again, and multiply the result by minus z. So that is the property multiplication by n, that is n raised to k. Now next one is division by n. So z transform of f of n upon n is equal to the integration z to infinity z inverse f of z dz. Now we will consider this. So by definition of z transform of f of n upon n is given by summation n runs from minus infinity to infinity f of n upon n z raised to minus n. Simplify the term. Therefore, that z raised to n upon n will be replaced by integration z to infinity z raised to minus n minus 1 dz. Now take this integral sign outside of the summation sign. So that will give us integration from z to infinity, and we will take z raised to minus 1 outside of the summation sign. So z inverse summation n runs over runs from minus infinity to infinity f of n z raised to minus n dz. If we see this term with the summation sign, then this will be f of z. Therefore it will give us z transform of f of n upon n is equal to integration from z to infinity z inverse into f of z dz, which is the required property, that is division by n. Now next is z transform of e raised to minus n into f of n. This is given by f of e raised to a into z, that is in the z transform of the sequence f of n, that is f of z, replace z by e raised to a into z, or z transform of e raised to n into f of n is given by f of e raised to minus a into z, that is in the z transform of the sequence f of n, that is f of z, replace z by e raised to minus az. So in this way we will evaluate this. So in the to prove this, we will consider the first one. So f of e raised to az is equal to, by the definition of z transform, it will be summation n runs from minus infinity to infinity f of n e raised to a into z raised to minus n. So simplifying this, we will be getting summation n runs from minus infinity to infinity e raised to minus an f of n z raised to minus n, which is the required result. Means from the definition of z transform, this can be written as z transform of e raised to minus an f of n, which is the required property. Okay, basic theorems. In that initial value theorem, if z transform of f of n is f of z, then f of 0 is equal to limit z tends to infinity of f of z. And the final value theorem is, if z transform of the sequence f of n is f of z, then limit n tends to infinity of f of n is equal to limit z tends to 1 of z minus 1 into f of z. For what purpose these two theorems will be used? Okay, so if we don't know what is the given function is, okay, or the sequence f of n, then from the z transform of that sequence, suppose the z transform is given f of z, then from that only we can evaluate the initial value of the function, that is f of 0, and the final value of the function, that is limit n tends to infinity of f of n, without knowing actual function f of n. So that is the use of this basic theorem, that is initial value theorem and final value theorem. And last theorem is convolution theorem. Suppose there are two sequences f of n and g of n whose z transforms are f of z and g of z. Then the convolution of these two sequences is defined as f of n star g of n, and which is defined as summation m runs from minus infinity to infinity f of n g of n minus m, or it is similar to summation m runs from minus infinity to infinity g of m f of n minus m, which is again the convolution of the sequence g of n star f of n. Then in this case, the z transform of the convolution of two sequences is z transform of f of n star g of n is equal to the product of their z transform, that is f of z into g of z. So in this way, this theorem, convolution theorem, will be used, and it plays important role in the solution of the difference equation and in probability problems involving sum of two independent random variables. So this is all about properties and theorems of Z transform. I hope you have understood this. Thanks for watching this video.